Okay.
Hi, hi everyone. Good morning, good afternoon, good evening, good day, wherever you are. I hope everything is fine with you and your loved ones. Thank you and welcome to the Geoscience and Geoenergy webinar of 15th of April 2021. Sebastian and I are delighted and pleased and honored to host our dear colleague Tad Patzek from KAUST. Tad Patzek is a director of the Ali Al Naimi Petroleum Engineering Research Center and professor of petroleum and chemical engineering at the King Abdullah University of Science and Technology, KAUST, in Saudi Arabia. Until December 2014, he was professor and chairman of the Petroleum and Geosystems Engineering Department at the University of Texas at Austin. Between 1990 to 2008, he was a professor of geoengineering at the University of California at Berkeley. Prior to joining Berkeley, he was a senior reservoir engineer at Shell Western E&P in Bakersfield, California, and also a senior research scientist at Shell Research Center in Houston, in Texas. Professor Patzek is also a presidential full professor in Poland, highest honor, and a distinguished member of the SPE, Society for Petroleum Engineers. By education, he is a chemical process engineer and physicist trained in catalysis and computational fluid mechanics. In 1983, at BRC, the Shell Research Center in Houston, two UT professors, Larry Lake and Gary Pope, introduced Todd to petroleum engineering, and his wife was never the same. So Larry and Gary converted him from chemical engineering to a petroleum engineering scientist. Todd has engaged in the studies of complex systems, focusing on the human factors in ultra-deep water offshore operations. He briefed Congress on the BP Deep Water Horizon well disaster in the Gulf and was a frequent guest on NPR, ABC, BBC, CNN, and such programs. In January 2011, Patzek became a member of the Ocean Energy Safety Advisory Committee for the Department of Interior's Bureau of Safety and Environmental Enforcement, BSEE. He co-wrote a popular book with a famous historian, Joseph Tainer, drilling down the Gulf debacle and our energy dilemma. In 2014, Professor Patzek, Michael Marder, and Frank Mail received the Cozzarelli Prize from the National Academy of Sciences in US for the best paper in engineering in gas production in the Barnett Shale obeys a simple scaling law. So those papers which simplify things and make it more impactful than making it overcomplicated. Since 2003, Professor Patzek has engaged in the studies of sustainability and industrial, agricultural, and agrofuel systems, all viewed through the lens of ecology and irreversible thermodynamics. Professor Patzek's papers in this domain are among his most cited papers and publications. In 2007, Todd participated in the OECD ministerial meetings in Paris that coped with the new biofuel mandates established in the US. For his work, Professor Patzek received the Erasmus Award, the Desiderius Erasmus Award from the EAGE, European Association for Geoscientists and Engineers, in 2020, last year. For the last 8 years, he has maintained a blog, Life Itself, about the environment, ecology, energy, complexity, and human activities with some 725,000 unique readers. Todd has co-authored over 300 papers and reports and has authored 5 books. It's a pleasure and honor to host you, Todd. I read all these achievements and see long way ahead of people like myself. So it's thank you very much. It's a pleasure to host you. Thanks for graciously accepting our invitation. To the audience, please note, Todd's lecture would last for about 30 minutes, but we just noticed he would speak a bit longer than that, which would be absolutely fine. And then after the lecture, the session will be handed over to Sebastian for discussion, questions and answering part. Please do post your questions in the chat box. Don't wait until the end of the lecture. Your questions may trigger other questions as well. As we know in academia, avalanche phenomena will take place that way. So do post your questions anytime you feel appropriate. And after the lecture, we will host a discussion session. So once more, thanks very much, Todd. Please, the stage, the bandwidth, the screen is all yours. We are looking very much forward to hearing your talk.
Well, thank you, Hadi, very much for this effusive introduction. I probably didn't deserve it. But what I'm going to talk about today will be an extension and a follow-up on the work that actually got attention of few people some 7 years ago when this PNAS paper was published. As you will see, since then, we've added the generalized extreme value statistics to the treatment of large sets of wells, and we've looked at much more geology. And of course, this presentation is with my student, Vardhana Saputra, research engineer Wissam Kirati, with David Hughes, a dear friend and a petroleum engineer who now works in the Post-Carbon Institute in California, and of course myself. The direct update of the PNAS paper was published, I guess, 2 years ago in the Energy and Fuels, and you can look it up. It's publicly available. It introduces the entire treatment that we use now to evaluate all shales in the US, including the Permian Basin. So why did I pick Marcellus? Well, it's #1 gas producer in the US and about 25 out of 90 billion standard cubic feet per day. It's the #1 largest shale play in the US, third largest natural gas field in the world. Now, I don't want to lose time, but these estimates of who's the largest are quite inaccurate. So the South Pars, the North Dome field, is supposed to contain about 35,000 cubic kilometers of gas. So these will be the first two ones. And then Marcellus should follow with 14.2 thousand cubic kilometers of gas. And Urengoy in Russia is about 6 to 11,000 cubic kilometers. I will show you that these numbers, especially as they pertain to shales, are highly uncertain. The extent of the play is huge, giant. It's the size of the United Kingdom, most appropriately for Sebastian. It was named after a little town of Marcellus in Onondaga County, New York. And of course, the town itself was named after Marcus Claudius Marcellus, a famous Roman general and consul whose coin you see on the right. I always like to define things, so I use actually this definition from a young geologist, Janelle Pfeiffer. Shale is nothing more than mud that has been compressed until it turns to stone, a process that takes millions of years. The Marcellus is a black shale, the black coming from marine organic matter compressed inside the mud. That is a lovely, very picturesque definition. And by the way, on the right, you can see the outcrop being fractured in every which place. And of course, these fractures introduce much higher permeability, especially if they are coupled with hydraulic fractures. So this is the extent, so the land area, which is underlain by the Marcellus shale, the black shale you just saw. And as I said, it's giant. But you will see that the productive area, which according to EIA is the broken line inside of the green area, okay, so the play extent, not just the shale extent, is still too large. And we will be kind of zooming and cutting back on all of these estimates. And as you will see, this play extent is not quite true according to what we understand it to be. Then the elevation contours also tell you a story from the kind of greenish color which you see in the northeast. The shale outcrops and is above the ground level. So even though there is lots of it, it's unusable because it has no gas and it's too shallow. So the deeper the better, right? And the average thickness of shale, as you will see in the deep parts, is less than 250 feet or so. So here are the contours of thickness, and as you see, Marcellus really is between 25 on the edges and 200 feet on thick only, and the largest thickness up to 900 feet is where it outcrops, but that is rather for the geologists and the tourists, not for petroleum engineers. So again, large area, very reasonable thickness. Now let's go and focus it a little bit. So if I look at the transects AA prime, BB prime, and CC prime, I don't know if you see my cursor. I hope you do. Do you?
Yeah, yes, we do. Yes.
Okay. So you see, AA prime is about 200 plus kilometers, and the shell goes from 0 to 6,000 feet of depth. BB prime is about 400 kilometers, and again from minus 1,000 to 6,000 and to 0 on the west. And then, of course, the CC prime is probably 12 or 1,500 kilometers, and again it goes down to 6,000 feet and then climbs up in New York to 0 to the outcrop. So I just want you to appreciate how large this play is. It's giant. It's a country. The US Geological Survey got in the action relatively early, and in 2019 devised, based on geology, 6 assessment units or AUs, which they use for all shales. And then we follow them plus minus, and we change sometimes what they do. And so their assessment is heavily based on thermal maturation and richness of source rock. Okay, and the interior AUs, the assessment units, are always better than the margin or fold belt AUs. And I will bring your attention to something that looks like a sperm whale head, this thing here, and then the one that is to the southwest of it, because these are the 2 most important pieces of the Marcellus shale. And of course, you will see that they are far smaller than the Energy Information Administration's assessments. But we kind of don't trust anyone, even ourselves. So what we do, we base whatever we work on production. And so what you see here are where people chose to drill wells, some 12,200 wells in all. And you can see the whalehead is the northeast core area, as we call it. The oval to the southwest of it is what we call the southwest core. The area where people still drill semi-decent wells, and we more or less outline it in orange, that will be, the differential would be the non-core area. And the difference between our non-core area and the black dotted line, which is the EIA play boundary, we call it the outer area. Also in gray, you will see the big cities, so for example, Pittsburgh here, and then there is Cincinnati, to the northwest, and so on. So this is a fairly densely populated area. So many of the shale areas will be excluded because of human settlements, farms and roads and what have you. And again, you will see that in the core area, the wells show in bright red. That means that they produce between 6 and 60 million standard cubic feet per day. Kind of the orangey wells are between 1.5 and 6, and the black wells are essentially duds. There's very few of them. Actually, you will see how few there is, and that's the outer area with absolutely non-productive wells. And just for comparison, I'm showing you to the left the USGS delineation, and to the right our delineation, which is actually a subset of the USGS delineation because it's based on where people can produce. And we don't care, about anything else from our point of view. So what about the wells? Well, people started drilling earlier on vertical wells, which show here kind of in a reddish color. There were about 2,000 of them. They last for a long time, so they're good, but they're not productive. And then around 2010, 2009, people started drilling horizontal wells, and by now there's over 12,000 of them. So that's the number of wells. When you look at the production from the vertical wells coincides with the x-axis. You don't see it. It's so little that they are completely irrelevant compared with the horizontal wells. So from now on, we understand that the vertical wells can be safely excluded. We ignore them as completely non-productive. Now, people make a big deal about progress of technology in shale drilling and well completions, and it's true. And it's clearly visible in Haynesville and in Marcellus. So here we picked data from a public domain but very disorganized database, which is called Frac Focus, and also from a private, much better organized database, which is called Drilling Info, and some other sources. And we've looked at the length of the laterals and the number of fracture stages, how much water was injected per foot of well lateral, and how much proppant was injected per foot of lateral. So let's start from the upper left. You can see that on average, the lateral grew from not quite 4,000 feet to a little bit over 8,000 feet. And the red line is P10, so 90% of laterals are shorter. And the blue line is P90, so 90% of laterals are longer than this line. So roughly doubling in time. If you look at the number of stages, they varied from around 10 in 2010 to close to 60 in 2020. And for comparison, we also included data from other independent sources just to calibrate that we're about right, or they are about right, or we both are right. In terms of fracturing water intensity, in terms of gallons per foot, right? We started injecting in, let's say, when it stabilized in 2012, about 1,100 gallons, and we went up to about 1,800 gallons per foot in 2020. In terms of the proppant intensity, pounds per foot, we started from 1,200 pounds per foot in 2013 when the data became available, and we ended up with close to 2,000 at around 2018, with a slight decline towards 2020. So we can see that the lateral length doubled, the number of frac stages sextupled, and the fracturing intensity almost doubled in all wells. So these are giant, I stress, giant industrial operations. Drilling of each well takes many train loads worth of water, proppant, and material. I don't know how many of you observed drilling of a large horizontal well, but it's a experience you shall not forget. Neither would the neighbors of that well. So what do we do now? We have the Marcellus Shale. We have delineated the northeast core, the southwest core. We have subtracted from it, kind of productive Marcellus non-core, so it's everything else within the orange contour. And we left the rest of it as the outer Marcellus, so between our orange contour and the dotted black line by EIA. And in each of the reservoir quality set, we have delineated 4 temporal well samples. So we would delineate wells that were completed between 2009 and 2012, 2013 and 2014, 15, 16, 17, and 20. And we would do it for all 4 reservoir quality classes. So altogether, it's 4 times 4. We have 16 statistical well samples. And as it turns out, they are statistically quite uniform within each class. So altogether, we are dealing, or at the time we wrote this, we dealt with 12,138 wells. It hasn't changed much because drilling has slowed down. So we now want to, so we have 16 well cohorts. Each cohort is, 1,000 or fewer wells. And we want to replace each 1,000 of wells, we want to replace with 1. And that 1 better be representative of 1,000 cousins, okay? So to do that, we use a combination of statistics and physical scaling. And this combination turned out to be, in my mind, the most powerful approach today among all involved in characterization of shales. So how do we do this? Well, we capture all the wells, let's say, as an example, within the southwest oval, the southwest core, and we start in 2015, 2016, and we have 1,147 wells. We look at the distribution of what these wells are producing per year, per well, and we fit it with a generalized extreme value distribution, which is probably not quite a fresh air distribution in this case. We get a very thorough statistics on the parameters of the distribution at 95% confidence level. We also can integrate the PDF and get the CDF. And you can see that our CDF calculated in red and empirical in black absolutely coincide, overlay each other. So there we can pick up the P90, P50, and P10 wells after 1 year, and we can get a very strict confidence interval on how certain we are that we are it, and we can do it for all 3 wells. We just displayed it for the P10 well, and then we transfer this information as to how many these BCF per year these wells produce onto another graph. So at year 1, the P90 produced less than 1, the P10 produced 3, and forgive the change of colors because we like to use black for the mean. The P50 well, the most probable well, actually produced 1.8 BCF per year. And what we do now, we repeat this for year 2 of production of the same cohort of wells, right? So So we get a different number of wells. Sometimes some wells failed, some wells joined. We get also an exceedingly good fit, as you can see, and we transfer the information from the CDF onto a plot of production versus time. So we get the second set of points. And we continue for year 3 with the same cohort of wells. And then we continue for year 4 with the same cohort of wells. Now you can see we're getting fewer wells and there is more noise in the picture. And then we continue to the last data point, to year 5. And you can see there's a much bigger uncertainty, which is still very small, by the way. And we get a confidence interval which is wider, but still very narrow. And so now, from all of the statistical data, without anything else but using generalized extreme value theory, we have constructed well prototypes with the P10, P50, and P90 rates versus time. So that's our statistical data for the prototype, right? So we can integrate the data and we can get the cumulative production from all of these wells after 5 years. And we repeat the same procedure for all the remaining 15 cohorts. So altogether, we will have 16 such prototypes. Now, the question is that this prototype statistically is limited to the number of years for which we have data. So what do we do to extrapolate this prototype for 20 more years on production? So today, everybody knows the answer to this question. You use artificial intelligence and neural networks. And I say to that, nonsense. You use physics and modeling. Well, not quite nonsense. I can show you another story about this, but yes, not as good as people think. Okay, so you use basic principles of mass conservation and momentum conservation together to actually constrain this production in the future. And this is where our scaling from 2013, somewhat improved, is appearing, right? So since this all has been published, and we published now, I don't know how many papers in various aspects of this, so we idealized the lateral as a straight line, all the fractures as parallel rectangles, which are spaced by 2D and have common length of 2L and a height h. And out of this, we write a scaling equation from which we obtain the recovery factor, which is a function of dimensionless time. And the time itself is the calendar time divided by the pressure interference time, pressure diffusion time, which will be, from a little bit over a year to multiple years, depending on the play. Okay? And then, of course, this recovery factor also is equal to the produced mass. We don't deal with volume, okay? Divided by the accessible mass in place. I'm going to come back to this. Okay? And we write a diffusion equation. It's nonlinear because this diffusion coefficient depends on pressure or pseudo pressure, which we introduced as well. And then we also, for Marcellus, we note that in addition, in alpha, in addition to gas saturation, there appears gas adsorption because it's cool and has a very high specific surface area of organic matter. So we also have to introduce the adsorption coefficient. And of course, since it pertains to the solid, there's a 1 minus phi factor. And they're both multiplied by the gas viscosity and the gas compressibility, because gas compressibility is so much higher than the rest of the system that we can replace total compressibility by gas compressibility. Okay? And I can dwell a little bit more that rho adsorbed is the adsorbed gas density, while rho g is the normal free gas density. And I can come back to this if you have more questions. Okay, so we do all the math we estimate how important the adsorption is, and this adsorption is important for the Marcellus. That's another paper by Behzad Eftekhari, my second last student at UT Austin, and Michael Mulder and myself, where we've looked at the Marcellus and also at adsorption. And here in this presentation, we take the average adsorption case, so neither the highest nor the lowest. And you can see that if you plot 1 minus phi times the adsorption coefficient as a function of gas pressure, as you decompress your reservoir, you desorb more and more gas, and at lower pressures or around your wellbore, the adsorbed gas volume or desorbed gas volume in that case is about equal to the free gas volume in the pore space. So adsorption is very important, and it will make the production curve or the master curve for the Marcellus look different than all other shales. And I'll also will comment on this. There's a bunch of numbers, and I'll be more than happy to explain these numbers to you. They kind of represent the average properties of shale and natural gas in it, and I'll skip over them in the interest of time. I will come back to this very interesting plot. So we have now evaluated production in all major US shales, here just gas shales. So the Barnett, from which we started, Eagleford, Haynesville, Marcellus, and Utica. And the x-axis here is the dimensions time. So 10 is virtually infinity for most shales, except for the Marcellus, which keeps on desorbing. Okay, so Marcellus is the green curve. And the recovery factor is plotted on the y-axis, and it's either a little bit above 0.8 or below 0.8. So now, this is 80% of the gas that is connected to the wellbore. And you can ask a proper question, so how many percent of the gas in the geometrical area of the parallelepiped spanned by the fractures and the lateral? And the answer is roughly half. So the overall recovery per bulk volume of the reservoir spanned by the well and its fractures is about 32%, 35%. Okay? And here we agree with major oil companies and minor oil companies. They estimate it to be about the same. So what's interesting here is that the fit is extremely simple. We can do it in a spreadsheet. And the ultimate recovery is the factor C. And you can see it's around 0.8. Eagleford is lower. Eagleford is not a very good shale, production-wise. A is about 2/3 for all the shales and 1/2 for the Marcellus. So there's a square root of time here. Okay, and B is about between 1 and 3/4 for all shales. Okay, and so this is one average master curve per shale. So this is average of averages, and you can see how they are similar and dissimilar. So all of them are similar except for Marcellus, which has very large adsorption. And so now we used our scaling. You already saw the plot on the left with the P50, P90, and P10 wells. And now we extrapolate production of these wells, let's say to 20 years. We also use a nonlinear scale, which is essentially a square root of time. So here's square root of 5, but we plotted 5, 10, and so on, so that the initial portion of the curve will be a straight line, right? The behavior of the well in bilinear flow in infinite medium before interference. And somewhere here, you start seeing pressure interference, so about 6 years in this particular case. And we also deal, I won't comment on this, with the late time exterior flow. So this will be radial flow from outside of the parallelepiped spanned by the well, but the influence of the external flow is minor here. Okay, so we do that for everybody, and we end up with 16 well prototypes. And you can see that on the y-axis going down, you have northeast, southwest core, the non-core area, and the other or outer. And here you have the well cohorts of the progress of technology. And especially in the cores, you can see that the progress of technology has been quite substantial. And these wells can produce, close to 0.6 cubic kilometers, standard cubic kilometers of gas, or 15 BCF. That's a lot of gas. Okay. And as you go to the southwest core, it's not as productive. The gas is wetter. If you go to a non-core, it's less productive, and you don't see much progress of technology at all. By the way, you didn't see as much of it in the southwest core. And if you go to the outer, well, they're lousy and they're not improving. Okay, so that's about the summation I can give you. All right. So the second question, which is solely based on the production well data, is how long do these wells survive? Right? Do they survive for 20 years? And the answer is highly unlikely, except for the Bakken, in which wells easily survived 30 years. It's a very quiet region, wells seem to be stable. But in the shales, if you just plot how many wells drilled in 2009 survive after 1, 2, 3, etc., 10 years of production, you will see that that's about 80%. If you go to newer wells, they actually drop out of the picture faster. And there's a variety of reasons for that. Let me skip over them right now. The bottom line is that on average for all cohorts here, half of the wells will survive for, let's say, 15 years. And we approximate this with a parabola, which ends up at roughly 15 point something years. And we do it for all regions, which are actually plotted here. You can see the well survival is not all that good. And so it's unlikely to have many wells that will survive for 20 years. And usually people report production after 30 years. Okay? So if you take all of this into account, but for the time being, keep in mind only the existing wells, now we have, how many prototypes do we have? Do we remember? Okay, nobody can, everybody's mic is turned off. So we would have 16, right? This many well prototypes. So we apply each prototype to the region in which it applies. We time shift it according to which well is drilled at what time, and we add them up. And once you do that, the black curve is the actual field data. The red curve, which you can see or not see from behind, is our fit, our match. And if you do nothing, this is how they decline. Okay, and the key here to note is that they decline, let's say, from 25 to 12 and a half within 3 years by 50%. Okay, and if you integrate the black and the red curves, you're going to get the cum, and the cumulative production is about 80 TCF or 3,400 cubic kilometers. So this is our base or do nothing projection for the Marcellus. Okay, but it's obvious that that's not the case. We're going to do something in the future. So now we're going to come up with some scenarios for the likely futures of the Marcellus. Okay, and so the first question we ask, if I close my eye, put a pencil, let's say on the southwest core area, will I be able to drill a successful well? And it turns out not so quickly, my dear, because many areas are excluded by the urban areas. You see the blank areas otherwise. And so we can actually calculate how much area is excluded. In addition, there are some true dry wells, but essentially many of the cells in this polygon will not be available for future drilling. So we just lump them into a lumped factor of the probability of success. Okay? And then we have to say, all right, so now we have our area, we have the excluded areas for cities and villages and towns. I will show you also the directions of the hydrofractures, the laterals. The hydrofractures will be perpendicular to them, and you can see they go, south, east, northwest, and they change the direction as you go towards southwest. And then we also, in each cell, we capture the number of wells which have been drilled. Okay, so dark red here is up to 10 wells have been drilled. And then we ask the question, all right, so given the number of wells which exist in a given 1 by 1 mile cell, how many more wells can we drill? Okay, so obviously, for geometrical considerations, we do not go beyond 4 1 mile wells because of the length of their hydrofractures, and we don't want them to be in pressure communication, or 2 2-mile wells. Okay, so once we ask that question and we know the direction of the laterals, we can actually project how many more wells could be drilled per each cell. And it's actually a fairly involved calculation, believe it or not. And so we calculate this infill potential as its absolute value plus value. So if the infill potential is negative, then obviously the sum is 0. If it's positive, then we add 2 numbers divided by 2. And we multiply the outcome by the overall probability of success. Okay? And so here we just show you the areas into which we will be drilling new wells, how many existing wells there are in this area, in these areas, and what is the infill potential according to us. And the infill potential according to us is 97,000 wells. Okay, and the asterisk is telling you that in the outer area, this estimate is likely much, much too high, because nobody in the right mind would drill 66,000 wells in something that doesn't produce anything. Okay, so you can see there's a big caveat here already. This outer area for which Energy Information Administration in the US doesn't pause, just accounts for it as a fully functional area of the play. Okay. So now we look at how many wells are drilled, what's the rig count per month in Marcellus. So in the heyday, up until 2015, there were about 120 rigs on average. Then there were 80, and more recently there were 40. So we estimate that the likely future of the Marcellus will be drilling at the current number of rigs for several years. So 40, we're going to drill in the best areas. So we infill core. Then we're going to double the number of rigs and infill the less plausible but still possible area, which is the non-core. And then, of course, we could do it at 120 rigs, and we'll do the exercise, but we already indicate to you that is actually impossible. Okay? And so here are those different futures for the Marcellus. So historical data, current peak, do nothing, you go steeply. This is you infill the core, so these are the best wells. Then you have drilled out the core by about 2028, and then the sum declines. Then you switch at twice the number of rigs to the non-core, so you stabilize it as well, and then you finish at about 2036, and then that thing is declining, and then you go nuts and drill thousands of wells at 120 wells rigs per month, and even though you drill so many wells, the play keeps on declining because these wells are of so low quality. Okay? And so if we integrate all of these curves, so here's the historical data, do nothing, just the basic plus core infill, basic plus core plus non-core, and this we infill outer. So you can see those 66,000 wells for the outer area give you a minimal increment of production, and of course no one's going to drill them. And so the estimated ultimate recovery for the Marcellus we come up with is between 125 and 170 TCF, which is around 70 to 100 cubic kilometers, standard cubic kilometers of gas. And if you are a careful listener, you remember I just told you, but it was 14,400. So what did you do? Well, I guess we didn't follow the EIA. So if you look at the EIA predictions, they keep on drilling like there's no tomorrow. And in fact, and they use some statistical prototypes. And out of this, they get 310 TCF for the maximum recovery from Marcellus, which happens to be twice our recovery, which happens to be 14,400 cubic kilometers, which is then picked up by international agencies and tabulated as the official economically recoverable gas from Marcellus. And hence, it's the third largest gas field in the world. Even with half of it, it still is in the first four. So it's a giant gas field. But you can see the difficulties, and I hate to tell you, but in Urengoi or Jamburg, it's probably much easier to calculate the ultimate recovery, but I wouldn't be surprised that it's much lower than what the good Russians are telling you. And of course, the South Pars and North Dome fields are absolute giants that collected gas from this huge anhydride seal over hundreds and hundreds or thousands of square kilometers. So they're huge, and the reserves is 35,000 cubic kilometers of producible gas. We'll see how that goes. Right? So I'm almost done. USGS went the other way. They didn't update for technology, and their estimate is significantly below ours. So we are much higher than USGS and much lower than EIA. Right? And we also did a fairly sophisticated economic analysis of these wells. So here, there's the net present value at 5% and 10% on the right for the infill core wells, infill non-core, and the black one is infill outer. And infill core breaks even within the current range of gas prices. And by the way, when we prepared this view graph, that was about at least 8 months ago. The price was almost exactly the same as it is today. Okay, and so you can see that at 5%, this outer area doesn't break even at $7.2, and at 10%, it doesn't break even, goes beyond the plot. I think $12 or $13 per MCF. So not economical. Okay, and therefore, my last conclusion: Marcellus is surely the largest shale gas play in the U.S. But like in other shales, the best producing wells are concentrated in the small areas of the entire play, much smaller than the play outline. And we found that the total area of the Marcellus core, the southwest and northeast, is about 6,000 square miles, which is barely 10% of the total Marcellus area. Of the 12,000 wells that we captured, they will produce 80 TCF by 2030, and then the infill drilling will increase this number by 125 to 170, most likely 160, because this outer area will never happen. And of course, as I told you, our economic analysis shows that infilling the outer area is a joke. But this is what the EIA proposes. And USGS underpredicts EUR because they don't have money and they don't please everybody as much as EIA. And so they don't have time for people to update their predictions. And with this, I'm done and I'm open for questions. Thank you.
Thank you very much, Todd. I guess you can now exit the presentation mode so that you could see us. Excellent. So thanks very much for the great presentation. I see already questions posted. So Sebastian, please.
Yes, thank you very much for fascinating talk as always, Todd. And it's really great to see how you can use the richness of data sets these days to make interesting predictions about the future. And a lot of the questions focus on this. So I start with Florian, who was the first one in the chat, and his first two comments are actually comments. He says, thank you for the very interesting talk. It was great to get an overview of how you continued along the direction of your seminal PNAS paper. I frequently discuss this paper in my class, and future students will be excited to have access to this presentation. So thank you. Hopefully a lot of students will use that video and your talk for their future learning. So now for Florian's question, when you're extrapolating in corporate phenomena that are not tested in inverted commas in the data that you have, how confident are you in the parameters that go into these models?
Well, as one of the famous actors said, folks, this is as good as it gets. And he said that in a psychiatrist's office, by the way. So being a psychiatric patient, I can tell you that this is as good as it gets in the following sense. We are predicting the least squares future, the average future, which is the best future one can predict given the data in the sense of Chorin and his collaborators, okay? Now, we are also in a lot of parameter estimations, we are completely non-parametric. That is, we are driven by what the field data are telling us. For example, the well survival, that's completely non-parametric. We are also using statistics, but the statistics seem to be fitting the data so well that I am surprised myself. Why is it so good? Maybe because each production event from a shale is an extreme event, right? You wouldn't be producing unless you fractured, and you wouldn't be producing unless you've connected through the hierarchy of scales. And so it seems that this generalized extreme value theory does such a good job. So it tells us what is the expected average productivity of the well to which we scale to the master curve by adjusting the tau and the m, and that's how we get all the variability in the model. So the tau shrinks the production in the horizontal direction, the x-axis, right? And the m scales it in the y direction. So by changing tau and m, we can actually stretch and shrink an actual production curve and fit it to the master curve, which is not any different than your well decline data, your classical well decline or pressure transient analysis. So how certain I am? I would say 75%. Maybe better than 75%, but not much more. And it's not accounting for things that we haven't seen in the data, we haven't seen in any of the models, such as abrupt change, failure of wells caused by the change of stress, breakthrough of water, which happened big way in the Barnett. The Barnett is done not because there's no gas, but because of these big fractures broke through water-bearing formations. And so they are now water producers that also produce some gas. I would say in the Bakken, I'm actually fairly certain, we published 2 papers on the Bakken on the oil. I'm fairly certain that what we said is actually very true because it's a very uncomplicated picture. Tectonically quiet play, wells that last forever, actually mud rock sandwiched in between 2 shales, and then upper Three Forks, which is another mud rock. And I think that's fairly certain. Now, the truly fascinating case on which we are working is, of course, the Permian, but I let somebody else ask me questions about Permian.
I'm going to just follow up with a side question, because you hinted in, I think the Bakken is relatively homogeneous, if I got this right. If you go closer to our home, the North Sea, or your home, new home in the Middle East, which are also provinces with lots of wells, not as many as the Marcellus Shale, would such a statistical analysis also work in the Middle East with long production history, thousands of wells in the North Sea, or is it because the geology is more complex and you have water flooding and more complex recovery mechanisms that it becomes more difficult to apply it?
Right. So please remember that I would confine this analysis just to shales. So no water flooding, no highly permeable reservoirs. They are different babies. There's so many, such richness. So if you want a mixed wettability, lower salinity water flood or adjusted salinity, that's not this baby. It's far more complicated. Okay, but shales, I've looked at over 100,000 horizontal shale wells, and we've looked at 450,000 vertical wells in tight carbonates in the Permian, and they're kind of similar. Mm-hmm. It's just they all follow. If you look at this hyperbolic tangent fit, the exponents on the fit among the shales are almost the same. 1/2 or 2/3, 1/2 for Marcellus, 2/3 on the time exponent, and the other exponent is about 3/4 and 1 for the Marcellus. Okay, so when everything is said and done, with all this complexity and 100,000 wells and changing technology and what have you, the behavior is actually relatively simple because it averages over so many things. It's like your Grant Darcy's law that averaged on scales from nanometers to kilometers, and you get your average answer. And which stabilizes your answer, of course, because you have a grand average over a large volumetric support. So that's how I explain this to myself.
Thank you, Ted. So we're running slightly out of time, but I'm going to take 2 questions that still here in the chat. You commented, you had a side remark on machine learning, and you do physics-driven models. So Yuan asked, would you share your idea about comparisons between physics-driven models and machine learning in terms of prediction?
Yes. So, of course, I cannot stop my students from using machine learning. This is now in the air, and it's like COVID virus, they got the bug. So I hasten to say that I was one of the original network people in the petroleum engineering in 1994. It was so long before most of you were born. And I did my things with it, and some of them were successful, but I've learned one big lesson. So for simple classification, they're very good. For more complex phenomena, especially for dynamic changes in behavior, they're not so good. Okay? And so it is not to say that we haven't used neural networks to classify the wells in the shales, actually in 4 shales, and we've used some fancier things which we shall publish soon for everybody's consumption, and they're okay. It takes time, it takes a lot of art and training, and your extrapolation capability, I would say, is limited. because if something changes, but you could throw the same argument in my face, Sebastian. What about your extrapolation ability? How is it limited? Well, I agree. If something dramatic changes, then none of us knows anything, right? But I would say if you constrain everything based on mass and momentum, it's a little bit better constrained than if you constrain it based on the structure of an image, because in the end, how we do this, it's a very complicated grayscale image, which we analyze with all the parameters of the well encoded into the image. So it's an interesting little sidetrack, which actually does a good job. But I would say modeling comes first.
Yeah, thank you. And I think we shouldn't forget physics. At the end
physics. That's what I mean. Physics-based modeling.
Yeah.
Okay. Yes, right. Today, when you say modeling, people will see networks, neural networks. No, precisely excluding neural networks, physics, chemistry, mathematical-based mathematical modeling. Okay, to be exact.
I take one final question. This is from Hassan Mahani. Thank you for the great talk. Next to the data-driven method you used, was there any numerical reservoir simulation as well? If so, what was the expected ultimate recovery and how do they compare?
That's actually a very good question, to which I have a very simple answer. If you make the simulator kind of have similar parameters, the answer will come out exactly the same. Now with the simulator, exactly, I mean, the simulator overlays whatever we predict. Now, with the simulator, you can actually now investigate more complicated scenarios. So you can investigate complex fractures, changes in this, changes in that, and so on. So your world, your universe becomes larger, but in the end, and again, I'm not the first one to do the sensitivity studies. What matters is number one, permeability, number two, porosity and fracture size and fracture area, and so on. And then, of course, it scales directly with the lateral length. So when everything is said and done, the complex simulators actually give you answers which on average are identical to what we do. Mm. Only we can do it in seconds for 12,000 wells, and simulator can do it in seconds for one well or two wells. Okay? So they're self-consistent. That's all I can say. They can either be both right or both wrong, right? Given what may happen or may not happen in the future.
Thank you. So we sort of run out of time. So thank you to the audience for some great questions. Thank you, Tad, again for an excellent talk, for taking the time and presenting from quarantine on your way back to Saudi Arabia. Thank you for also answering the questions in so much detail. It's good having you on the call and on the webinar. So Hadi, over to you for some final.
Thanks very much. Yeah, very nice discussion as well. I'd like to take the chance to introduce our next week's speaker. Will be Jen Roberts from the University of Strathclyde from UK. Jen will present a talk on geosciences for the future. And I think it's going to be next week. It's going to be Earth Day, I think. So it's going to be, it's for future of geosciences. So until next week, 22nd of April, let's stay happy, healthy, and tuned in. And we see you all again with another geoscientific and geoenergetic talk. Thanks a lot, Todd, for being on your way back home from another home to another home somewhere, but still we could find you.
Away from home, yes. Okay.
Bye-bye. Thank you, everyone.
Bye-bye.